All right, so we look at symmetric matrices as our first subtopic in this video. Okay, so what do they mean when they say a symmetric matrix? Okay, so in that other video that you're supposed to watch, okay, that some of you didn't watch, we defined what a square matrix was. Okay, so a square matrix is simply a matrix that has equal number of rows and columns. So for example, if the order of the matrix, okay, the order of the matrix is 2 by 2, then we are going to say that is a square matrix because we know that the first number represents the rows, the other number there represents the column. So for example, if I write 2 there, 1, 4, maybe 5. Okay, this one here is a square matrix because the number of rows, I can count 1, 2, it's the same as the number of columns, 1, 2. Okay, so a square matrix is simply a matrix that has the same number of rows and columns. So in the definition of a symmetric matrix, okay, you always have to mention that the matrix that you're talking about is actually a square matrix. Okay, if you don't mention that it's a square matrix, you're not going to get the full marks for that particular question. Okay, so what are symmetric matrices? Okay, so here's the definition here. So notice how I'm starting the definition. So I'm saying let A be a square matrix. Very important concept. Okay, if you miss out this part here, then you're not going to get the full marks. Okay, so let A be a square matrix. Okay, then the matrix A is called a symmetric matrix if the transpose of that matrix is equal to itself. Okay, so that is the condition there. So if A transpose for this square matrix is equal to the matrix itself, then we are going to conclude that the matrix A is actually what? Symmetric. Okay, so what example can we give here for the symmetric matrices? Okay, it's very simple. Just get a matrix such that its transpose, okay, is actually the same as the matrix itself. Okay, so let's get this matrix here. So if, for example, I get a matrix 1, okay, 0, and then 0, and then 1. Will this matrix here be a symmetric matrix? Okay, will this matrix here be a symmetric matrix? Okay, let's try. So if this is my matrix A here, let's find the transpose. Okay, so the transpose, we defined it as exchanging the rows with the columns. So this here is the first row. This one is the second row. So the first row here, I'm going to write it as a column in this A transpose. So I'll say 1, 0. So I've written this 1 and the 0 as a column. Then this second row, I'll write it again as a second column here. So it will be 0, 1. Okay, so you can see that A and the A transpose, they are equal. Okay, if this condition is satisfied, then we can conclude that the matrix A is actually what? Symmetric. Okay, so another example is this one. So let's say I have matrix A is equals to, let's say 2, 3, 3, 5. Okay, so if I find A transpose here, it will be equals to, I interchange the rows with the columns. So this is the first row here. I write it as a column here to be 2, 3. Okay. This second row, I write it as a column, it will be 3, 5. So you see that A and A transpose, they're the same. So we're going to conclude that A is actually what? Symmetric. Okay. So if this condition does not hold, then we are going to say that our matrix A is actually not symmetric. Okay. But there are some questions where they're trying to test your understanding. They'll just give you a matrix like this. Okay, so I'll ask a question here to see if you guys are following. So I write 2, 3, 0. Okay. 1, 0, 2. Okay, let me write it like this. So 2, 3, 0, and then I write 0, 2, 3. Okay, so can this matrix here be symmetric? Anyone who can try. Can that matrix there be
But
symmetric?
it can't be symmetric because it's not a square matrix.
Okay, so very good. Exactly. So sometimes in the tests, in the exams, okay, your lecturer will just try to test your understanding of what a symmetric matrix is. They will give you a matrix which is not square. Okay, it's not a square matrix. And then they will ask you to show that it's a square matrix. So if you don't know this part of the definition, okay, you just start struggling trying to show it, but it can never be a symmetric matrix, okay, because it's not a square matrix. All right, so that is the definition. Let's look at an example. So the example doesn't come as simple as this. I was just using this to explain the concept. So let's look at an example. So the example can be something like this. Okay, so this example is saying, find all the values A, B, and C for which this matrix A is what? Symmetric. Okay, so we're just going to use the concept of symmetric in order to find the values of A, B, and C. So the matrix A, okay, is given here. So here I'm just going to write my matrix A transpose. So the A transpose will be the matrix where I've interchanged the rows with the columns, okay, because I'm looking for the transpose. So this is the first row here. I'll write it as a column here. So it will be 2 and then A minus 2B plus 2C and then 2A plus B plus C. So this was my first row here. It has become a column. And then this second row becomes the second column. So it will be 3, 5, and then A plus C. The third row becomes the third column. So it will be 0, minus 2, and then 1, 7 there. Okay, so this is my A transpose. Okay, since now they have said that this A is symmetric, then it means this here should be equals to the what? To the matrix what? A. Okay, so I'm going to say, let's write now the matrix A here because it's symmetric. So A transpose is actually equals to what? To A. So the A has a 2 there, and then A minus 2B plus 2C, and then 2A plus B plus C, and then 3, 5, A plus C, and then 0 minus 2, and then 7. Okay, you can see. So we have equated the A transpose to the A. And then using this now, I can actually find the values of A, B, and C. Okay, so these now are equal matrices. So we said in the definition of the equal matrices, if matrices are equal, okay, then all their entries or all the elements in those matrices are actually equal. So these two, you can see, it will be equals to these two. It's at the same position. These 3 here, it will be equals to everything that is there. So that will be our first equation. So it will be 3 is equals to A minus 2B plus 2C. This is 0 will be equals to whatever is there. So it will be 0 is equals to 2A plus B plus C. Okay, and then this this guy here will be equals to this 3, which is the same equation that we wrote here. So we can't write it twice, just write it once. The 5 will be equal to the 5. The minus 2 here will be equals to the A plus what? C. Then this guy will be equals to the 0, which we've already written here. A plus C is equals to minus 2. I've already written it. And then this 7 is equals to the what? To the 7. So you see that we come up with 3 equations that can help us to find the values of A, B, and C. So let's start, first of all, by making one of these to be a subject of a formula in this equation here. So I'll say, let my A be equals to, so I'll just get this C, take it to the other side. So it will be minus 2 minus C. So this is my A. And then I get this A, I put it into this formula and this formula. So for the first one, it will be 3 is equals to, where there's A here, I put minus 2 minus C, okay? And then minus 2B, and then plus C, 2C. Okay, so this will be my equation 1. So here I can remove the brackets. So it will be minus 2C minus 2B plus 2C. Okay, so 3 is equals to, here I can add the like terms now. So minus C here with plus 2, I'm just going to get a C. Okay, and then minus 2b. I'll write it here. And then this minus 2 can go to the other side. So that will be plus 2 here. Okay, so what I have there will be 5 is equals to c minus 2b. So this is the equation that I get in terms of b and c from this first one. Let's also get an equation from here. So this will be 0 is equals to 2. The a is minus 2 minus c, and then plus c, b plus c. So this will be 0 is equals to 2 multiplied by minus 2. That will be minus 4, then minus 2c plus b plus c. Like terms together. This minus 4 can come to the other side, so it will be 4 is equals to, like terms together, it will be b, this one, and then minus 2c with the c there is going to give me minus c. So this is another equation that I get in terms of b and c. So now I have this equation in terms of b and c, and this one in terms of b and c. So I can actually make this c to be the subject here. So I'll just say c is equals to, so I take this minus c to the other side, then I take the 4 to the other side. So it will be b is equals to, c is equals to b minus 4. So this b minus 4 is what I'm going to substitute into that equation. So let's create some space here. So I'm going to say 5 is equals to, this c here, it will be b minus 4, and then minus 2b. Okay, so meaning that this will be 5. This minus 4 goes to the other side to be plus 4 is equals to, this will be b minus this 2b. So that will give me what? It will be 9 is equals to minus b. And then I divide by minus 1, divide by minus 1, means my b is simply going to be equals to what? Minus 9. Okay, so I found my b, which is minus 9. I can now go on and find my c. So my c won't be very difficult to find. I'll just say c is equals to the b, which is minus 9, then minus 4. So this will give me a c, which is minus what? 13. Okay, I have my b, I have my c. I can now find my a. So a is just going to be equals to minus 2 minus minus 13. So be careful with the signs there. Okay, so some of you end up just putting 13. You have to put minus 13 there. So this will be, okay, let me create some space there. So that will be a is equals to minus 2 plus 13, which will just give me a is equals to what? 11. Okay, so a is equals to 11, b is equals to minus 9, c is equals to minus 13. Okay, so we can write those answers somewhere here. So we can say our a, 11, b, minus 9, and then c is going to be equals to minus 13. Okay, so those are the answers there. Any questions there on how we've used the concept of symmetric matrix to find the values of A, B, and C? Okay, so if there are no questions, we'll move on to the next one. Okay, so this one is the same like we did. So I'm going to leave it for you for practice. So it's saying find X, Y, Z such that A is equals to this much, such that this matrix here, A, is actually what? Symmetric. Okay, so you use the same principle there for the symmetric matrix. You are going to be able to find the values of X, Y, and Z. All right, so try it out. So you can take a screenshot. So take a screenshot and then you keep the question so that you can solve it. Okay, take a screenshot so that you keep the question so that you can actually solve it. Okay. All right, so I hope you've taken a screenshot. So go to the next one, which is the concept of skew symmetric matrix. Okay, so what is a skew symmetric matrix? Okay, so again, the definition should start with A being a square matrix. Okay, the definition should start with A being a what? A square matrix. Okay, so what we are going to say there is that let A be a square matrix. Okay, then the matrix A is called a skew symmetric matrix if the transpose of A is equals to the minus of what? A. All right, so if A transpose is equals to minus A, then we're going to say that the matrix that we have is skew symmetric. So for example, okay, if my matrix A is, let's say 0, 2, minus 2, and then 0 there. Okay, so let's find A transpose. So A transpose is going to be, this column becomes the row. So it will be 0, 2. This row here becomes the second column to be minus 2, 0. Okay, so this is my transpose. And then let's find minus A. So minus A is simply scalar multiplication of this matrix with a minus 1. So I'm multiplying this matrix here with a minus 1. So if I multiply the 0, I'm getting 0. If I multiply the 2, I'm getting minus 2. If I multiply the minus 2, I'm getting positive 2. If I multiply the 0, I get 0 again. So you see that A transpose is actually equal to what? To the minus A. So if this is true, then we conclude that our matrix is what? Skew symmetric. As simple as that. All right. So even here, they can bring that question. They'll give you a matrix which is not a square matrix. And then they'll ask you, show that it is skew symmetric. Okay. So the answer there will just be, this matrix cannot be skew symmetric because it's not a square matrix. All right, but if you don't know the definition there, then it's going to be a bit difficult for you to actually find the correct answer. All right, so let's look at a question from the exam papers. Okay, so here they're saying find the values of x and y such that the matrix given here is skew symmetric. Okay, find the values of x and y such that this is skew symmetric. So first of all, we just have to find A transpose. So A transpose will be 0, x, and then 4. Okay, minus 2, 0, y, and then minus 4, minus y, 0. So what I've done, I've just changed these rows here into columns. Okay, and then this should be equal to the what? To the minus of A. Okay, so the minus of A is multiplying each of these entries with a negative. So it will be 0 there, minus x, minus 4. This will be plus 2, 0, minus y, positive 4, positive y, 0. So I've just multiplied each of these entries here with a negative number, which is a negative 1. Okay, and then from there, how can we find the value of x and y? So these things are equal. Okay, so this is minus x. So if they are equal, then their entries are also equal. So you can see 0 there, 0 there. And then this minus 2 here should be equals to the minus x. So I'm going to say minus x is equals to minus 2. Divide both by negative 1. You're going to get x is equals to positive 2. So x is equals to positive 2. What about the y? Okay. And you can also see here x is also equals to positive 2. Okay. So meaning that the y is going to be equals to what? Okay. So y here, there's y here. Okay. And then there's also y here. Okay, so I can equate those. So minus y is equals to minus y, definitely. So divide both sides by negative. Here you have y is equals to y. So what is the answer for y? Okay, so this simply means y can be any number that you think of, as long as it's a real number. Okay, as long as it's a real number, you can put it there and it still be a skew symmetric matrix. You can also see here y is equals to y. Okay, so we can't find the actual value for the y, but we can just state that y will be a real number. So how do you represent that in your answers? You say x is equals to 2, but y is any real number that you can think of. Okay, so this one here will be the answer. All right, so any questions there, guys, on the skew symmetric? Okay, so let's look at another question here. So here they're saying determine whether the following matrix is skew symmetric. Okay, so for us to determine if this is skewed symmetric, we just have to find, first of all, A transpose, which will just be 0, 4, minus 4, 0, okay? And then minus A, it will be equals to 0 minus 4, 4, 0. And we see that these are equal, okay? So it's right, since A transpose is equals to minus A, then A is skew symmetric like that. Okay, so that is the concept. So I'm trying to use very basic examples so that you just get the concept. And then once you get the concept, we can now move on to find the harder questions. Okay, so I hope you've understood the concept. And then also in this course, it is a it is a mathematics course, and this is fun. It's a mathematics course, okay? But in your tests, your quizzes, you are going to be having a section where you have multiple choice questions and also true or false questions. Okay. So if you don't understand the concept, then you cannot answer the true and false questions because they'll be asking you, like you'll be given a statement and then they'll ask you, is this statement true or false? Okay. When you say true, you have to justify why you are saying it's true. If you say false, you also have to justify why you are saying false. Okay. So if you don't know the concept, there's no way you're going to answer the true and false question. The multiple choice you can guess and get the correct answer, but the true and false, they'll read your reason. Yeah, they will need your reasoning. Okay, so make sure you understand the concept. And then we move to the orthogonal matrices. Okay, so orthogonal matrices, these are very nice matrices. Okay, so by orthogonal matrix, we simply mean that a square matrix A, okay, we have its transpose equals to its inverse. Okay, we have its transpose equaling its inverse. So you can see the definition here. I was saying a square matrix A. Don't forget this word here. Okay, square matrix A is called an orthogonal matrix if A transpose is equals to the inverse of A. Okay. So I know you know how to find the inverse from first year. Just the did you do 3 by 3 matrix? I think you did, yes. So the 3 by 3 matrices you did. Okay, the inverse, the 2 by 2, I know you know from grade 12. So if the transpose is equal to the inverse, then we conclude that okay, this matrix is what? It's it's a an orthogonal matrix. Okay, so for example, A is equals to 0, 1, 1, 0. Show that this matrix is orthogonal. Okay, what we need to do is just show that A transpose is actually equal to A inverse. So A transpose won't be hard to find. It will just be this row becomes the first column. So 0, 1, and then this row becomes the second column, 1, 0. So that is my what? My my A transpose. Okay, what about my inverse? Okay, so the way we're going to be finding the inverse sometimes, okay, sometimes you'll be given a very big matrix and to be impossible for you to compute the inverse, like using the same uh, usual algebraic method that we use. Like we find first the determinant, and then you find the adjoint, and then you multiply 1 over the adjoint, I mean 1 over determinant multiplied by the adjoint, then you find the inverse. It's going to be hard. So for us to prove that something is orthogonal, we are going to be using a very simple trick. So that trick is that, okay, if A is a matrix, I multiply it with its inverse. Okay, this should always give me the identity matrix for that order of matrix that have been given. So this one here is a 2 by 2 is a 2 by 2 matrix. This one here, it has 2 rows and 2 columns. Okay, so if we are saying that this transpose is equal to the inverse, okay, then if I multiply the this transpose, okay, with the matrix A, okay, and it gives me the identity, then it proves that actually the matrix is what? Orthogonal. Okay, so this rule here, take note of this rule here. If I multiply a matrix with its inverse, I get the identity. It's the same as when I multiply 10 with 1, I'm still going to get 10, right? Okay. If I multiply what? No, this is not the correct example. That one is the identity, but that I want the inverse. So if I multiply 10 with 1 over 10, I'm going to get what? 1. Okay, so this guy here, the 1 over 10, is the inverse of 10. So now when it comes to matrices, 1, okay, the 1 is called as the identity matrix. So the identity matrix is the 1 when it comes to the matrices. So when I multiply a matrix with its inverse and then I get the identity, then it means that this guy here is indeed, it's what? It's inverse. So what I'm going to do here, I'm going to say A multiplied by the A transpose. So this will just give me 0, 1, 1, 0. Okay, multiplied by the A transpose is here, which is 0, 1, 1, 0 as well. So let's multiply. I know you know how to multiply matrices, right? So you do a row by column. So 0, so it will be this row multiplied by this column, this row again multiplied by that column. Okay, so it will be 0 multiplied by 0. That's just going to be 0. And then 1 multiplied by 1, okay, I'm going to get 0 plus 1, that will be 1. 0 multiplied by 1, it will be 0, plus 1 multiplied by 0, it will be 0 again. I write 0. 1 here, I've moved to this row now. 1 multiplied by 0, it is 0, plus 0 multiplied by 1, it is 0. So I put 0 there. Then 1 multiplied by 1 plus 0 multiplied by 0, that will be 1. So you see that if I multiply this A with this transpose, I'm getting the identity. This is the identity for the 2 by 2 matrix. So by identity, we mean that all the entries in the main diagonal here are going to be 1, and then whatever is left is just going to be 0. Okay, so if you watch the video that I sent in the morning, we defined what the identity matrix was. Okay, so you can see here that when I multiply this A with its transpose, I'm getting the identity. So it means that whatever is here is equals to the inverse. Okay, so it means that this guy here is actually equal to the what? To the inverse, which is A minus there. Okay, so hence proved. So that's how you can show. But if you want, okay, you cannot use this proof. You can still just go on and find the inverse of this guy. Since this one is just a simple 2 by 2 matrix, so you can find first you can find the determinant. Okay, after you find the determinant, you find the adjoint. Okay, after you find the adjoint, and then you go on to prove that the inverse is actually equal to the what? To the A transpose. So that would say that the matrix is orthogonal. All right, so that's how we can prove. And then here, there's also another question here. So we can try to prove this as well. So prove that that matrix is orthogonal. So the first thing I'll say, okay, let this matrix be matrix A is equals to. So I'll just find the transpose of this matrix. So A transpose will be the row here becomes the column. So it will be cos theta sine theta. This second row becomes the second column to be minus sine theta. Okay, and then cos theta. Okay, so this one here is my A transpose. Okay, so I have to show that the A transpose is equal to the what? To the inverse of A. So for this one, I won't go by that proof that I did in the previous question. I'll try to just go by the normal method that you are used to. So I'll say, let's find the determinant of A. So determinant of A, it's the main diagonal minus the minor diagonal. So the main diagonal of cos and cos. So that will give me cos squared theta. Okay, and then I'll say minus, and then I multiply minus sine theta with the sine theta, I'll get minus sine squared theta. So you see that this will be cos squared theta plus sine squared theta. Okay, so this requires you to know trigonometry. Okay, so the guy was asking, do we have to know the topics? Yes, because we'll be using them in different courses. So you remember the identity here from first year? This is just what? 1. So the determinant there is 1. So I can write my determinant of A is actually 1. Okay, from there I need to find my adjoint of A. So the adjoint will be, okay, I just exchange the sign in this minor diagonal, and then I exchange the entries in the major diagonal. So in the major diagonal, I have cos, I have cos. So even if I exchange, I still remain with the cos and cos. Okay, and then, I actually have to use this because I'm finding the adjoint of A. Okay, and then there I exchange the sign. So this one was negative, here it becomes positive. How did I write the cos here? So this one has to be somewhere here. Okay, and then now I exchange the sign there. So this was negative here. Here it becomes positive. It was positive there, it becomes the negative like this. Okay, so now the inverse of A, remember the formula, it is 1 over the determinant of A multiplied by the adjoint of A. So this will be 1, the determinant is 1, multiplied by this adjoint here is this guy. So it will be cos theta minus sine theta, and then sine theta, and then cos theta. So you're going to be finding such questions in your tutorial sheets. Okay, so now let's compare. We see that my A transpose there is actually equal to the what? To the A to the power minus 1, or the A inverse, because this here is the same as this. Okay, so I'll just write it here, cos theta minus sine theta, and then sine theta cos theta. Okay, so since these are the same, we're going to conclude that this matrix that was given here is actually what? Orthogonal. All right, so any questions there, guys, on what we have done? Any questions there? Okay, so if there are no
Clear.
questions, I think that's